What if I told you that a single number, just 4 digits, is about to make diesel trucks obsolete forever, cost the fossil fuel industry hundreds of billions of dollars, and completely rewrite the rules of one of the oldest industries on Earth? That number is 1.55, specifically, 1.55 kilowatt-hours per mile. And it belongs to the Tesla Semi, a truck that PepsiCo, Walmart, Cisco, and some of the biggest logistics companies on the planet are already deploying in real commercial operations right now, and the real-world data coming back from those deployments is so extraordinary, it is almost hard to believe. Welcome back to DriveTech Tesla, the channel that keeps you ahead of every Tesla and EV breakthrough before anyone else, and today we are going incredibly deep on this 1.55 kilowatt-hours per mile figure. What it actually means in plain language, how Tesla achieved it when almost every expert said it was impossible, what it costs compared to diesel per mile and over a decade of operation, what it means for the trucking industry and the wider energy landscape, and why every major diesel truck manufacturer in the world is quietly panicking right now. So make sure you are subscribed to DriveTech Tesla and hit that notification bell right now, because this is the kind of story that changes how you see transportation forever. Let's get into it. To understand why 1.55 kilowatt-hours per mile is so extraordinary, you first need to understand the context, because we are not talking about a small car or a delivery van here. We are talking about a Class 8 heavy-duty semi-truck, the biggest, heaviest category of commercial vehicles on American roads. The kind of truck that can weigh up to 80,000 pounds fully loaded, haul enormous cargo across thousands of miles in all weather conditions, and has historically been one of the most fuel-hungry machines that humanity has ever put on a road. A typical diesel semi-truck gets somewhere between 5.5 and 7 miles per gallon under real-world conditions, and when you translate that into energy terms, you are looking at roughly 1.8 to 2 kilowatt-hours per mile equivalent in total energy consumed at the wheel. Now think about that for a second. Tesla's electric Semi is consuming only 1.55 kilowatt-hours per mile in actual commercial operations, which means it is not just competitive with diesel trucks in energy terms. It is definitively more energy efficient than the best diesel semi-trucks ever built, and that is a genuinely staggering engineering achievement that deserves far more attention than it has been getting in the mainstream media. Now, let's talk about where this specific number comes from, because this is not a laboratory figure or a controlled test result, this is real-world operational data gathered under actual commercial conditions. PepsiCo was one of Tesla's first major commercial customers for the Semi, taking delivery of their first units back in December 2022 at a high-profile event at Gigafactory Nevada, making them genuine pioneers in commercial electric trucking history. PepsiCo has been running their Tesla Semis on established routes in California, hauling full loads between distribution centers and retail locations, driving on real roads with real traffic and real weather variations, and the data they have been collecting and sharing with the industry has been extraordinary and frankly world-changing. Their real-world energy consumption figures have consistently come in at or below 1.7 kilowatt-hours per mile across various route conditions, and under optimal conditions on flatter routes with experienced drivers using intelligent route planning. Some of their drivers have consistently clocked in at 1.55 kilowatt-hours per mile, a number that has genuinely shocked transportation engineers who spent decades assuming that electric trucks could never be this efficient at commercial scale. PepsiCo is not alone in validating these figures. Walmart, Cisco, and several other early adopters are reporting similar numbers from their own fleets, which means this is not a cherry-picked anomaly from one particularly good day on one particularly flat road. This is a repeatable, reproducible, real-world performance figure that the Tesla Semi is genuinely capable of achieving under normal commercial conditions, and that changes everything. So how did Tesla actually achieve this? Because it absolutely did not happen by accident. It required years of engineering innovation, billions of dollars of investment, and parallel breakthroughs across multiple disciplines simultaneously. And when you look at the individual elements that Tesla brought together into the Semi's design, you start to understand why this truck is so fundamentally different from anything else on the road today. Let's start with aerodynamics, because this is where Tesla made some of the most dramatic improvements over conventional truck design. Traditional semi-trucks are essentially rolling bricks, They are designed primarily for maximum cargo capacity and structural durability, and aerodynamics has historically been an afterthought for most truck manufacturers, with only minimal aero kits and deflectors added as aftermarket improvements. The average diesel semi-truck has a drag coefficient somewhere between 0.6 and 0.7, which is genuinely terrible by modern engineering standards. For context, a modern passenger car typically has a drag coefficient between 0.25 and 0.35. Tesla's Semi, by contrast, was designed from the absolute ground up with aerodynamics as a primary engineering priority, with the entire exterior shape optimized around the goal of minimizing air resistance at highway speeds where aerodynamic drag accounts for the majority of a truck's total energy consumption. The cab is streamlined, the front face is carefully sculpted, the connection between cab and trailer is tightly optimized to prevent air turbulence, the underbody is smooth and sealed, and the overall shape of the vehicle is designed to slice through air rather than bulldoze through it. The result is a drag coefficient that Tesla has stated is lower than that of a Porsche 911 sports car, a remarkable and almost unbelievable achievement for a vehicle of this size and commercial category. Then there is the drivetrain architecture, which represents an equally revolutionary departure from conventional truck design. Traditional diesel trucks use a single large diesel engine connected through a complex and heavy multi-speed transmission to the rear axle, a system that is inherently inefficient because of all the mechanical losses involved in converting combustion energy into wheel rotation through multiple gear sets, driveshafts, and differentials. Tesla completely discarded this entire architecture. The Tesla Semi uses 4 independent electric motors, 2 on each rear axle, derived directly from Tesla's highly refined automotive motor program, which means they benefit from years of engineering iteration and real-world optimization. Each motor can be individually controlled by the vehicle's software with millisecond precision, meaning the truck's control systems can continuously and dynamically optimize power delivery from each motor to maximize overall system efficiency in real time based on speed, load, gradient, and many other factors simultaneously. And critically, when the truck is decelerating or descending a hill, all 4 motors instantly flip into regenerative braking mode, capturing kinetic energy that would otherwise be wasted as heat in conventional friction brakes and pumping it back into the battery pack for use later in the journey. Electric motors are inherently more efficient than combustion engines in converting energy input to wheel torque. A best-in-class electric motor can convert 90 to 95% of electrical energy input into useful mechanical motion, compared to only around 35 to 40% efficiency for the very best modern diesel engines, and Tesla's motors sit right at the top of that efficiency range, built in-house with precisely optimized copper windings, magnetic materials, and thermal management systems. The battery pack in the Tesla Semi is another engineering marvel. A 500-plus kilowatt-hour energy storage system that enables the 500-mile range variant to haul a full legal payload of 80,000 pounds across long distances without requiring an intermediate charge. The battery pack is integrated structurally into the frame of the truck in a way that actually improves its overall structural rigidity and significantly lowers the center of gravity compared to a conventional diesel truck, making the Tesla Semi inherently more stable in corners and emergency maneuvers. And unlike a diesel fuel tank that gets progressively lighter as you burn through it, changing the truck's weight distribution and handling characteristics throughout the journey. A battery electric truck maintains essentially constant weight from start to finish, which simplifies load management for drivers and improves handling consistency. Now, let us talk about what 1.55 kilowatt-hours per mile actually means in real dollar terms, because this is where the story gets truly compelling for any trucking company doing the financial analysis seriously. In the United States, commercial electricity rates for large fleet charging operations typically range from approximately 8 to 15 cents per kilowatt-hour depending on the region, the time of day charging occurs, and the specific utility agreement the company negotiates. At 1.55 kilowatt-hours per mile and even a relatively high commercial electricity rate of 12 cents per kilowatt-hour, the fuel cost per mile for the Tesla Semi works out to just 18.6 cents. Now compare that directly to a diesel semi-truck achieving 6 miles per gallon with diesel prices ranging between $4 and $5 per gallon, that is 67 to 83 cents per mile in diesel fuel costs alone. The Tesla Semi's energy cost per mile is roughly 75 to 80% lower than a diesel equivalent, and over a typical semi-truck's annual operational mileage of 100,000 to 150,000 miles, that represents a fuel saving of between $50,000 and $100,000 per year, per truck. That number alone is extraordinary and would justify the investment in electrification for most large fleet operators, but the savings do not stop at fuel. Maintenance costs represent another enormous operational advantage for the Tesla Semi that is frequently underestimated in public discussions. A conventional diesel semi-truck has thousands of moving mechanical parts. Pistons firing hundreds of times per minute, intake and exhaust valves, a complex multi-speed transmission, turbochargers, cooling systems, exhaust aftertreatment systems, and DEF, diesel exhaust fluid, dosing systems, all of which require regular maintenance, all of which wear out over time, and all of which can and regularly do fail in ways that require expensive repairs and cause costly downtime. A Tesla Semi has a dramatically simpler drivetrain with far fewer moving parts. There is no transmission to service, no engine oil to change, no complex exhaust aftertreatment system, no DEF fluid to refill, and the regenerative braking system means the physical brake pads and rotors wear far more slowly than on a diesel truck. Industry analyses consistently suggest that electric trucks can cut maintenance costs by 40 to 70% compared to diesel equivalents over their operational lifetime, and when you combine those maintenance savings with the fuel savings over a 10-year operational life, a single Tesla Semi can represent a total cost of ownership advantage of $500,000 to $1 million compared to a comparable diesel truck. And that figure does not even account for carbon credits, regulatory compliance advantages, or the brand and sustainability value that comes from operating a visibly zero-emission fleet. The competitive context is critically important here, because Tesla is not the only company that has recognized the enormous market opportunity in electric heavy trucking. Freightliner has the eCascadia, Volvo Trucks has the FM electric and FH electric platforms, Kenworth and Peterbilt have developed electric variants of their flagship models, and several startups have been promising to disrupt the market. But here is the uncomfortable reality that every competitor has to reckon with: the 1.55 kilowatt-hours per mile efficiency figure that Tesla is achieving in real commercial operations is significantly and materially better than what most competitors have published for their competing products. The Freightliner eCascadia has been reported at energy consumption figures closer to 2.0 to 2.2 kilowatt-hours per mile in real-world use, more than 30% worse than the Tesla Semi's best numbers. At scale, across a fleet of hundreds or thousands of trucks each operating 100,000 miles or more per year, the difference between 1.55 and 2.0 kilowatt-hours per mile in energy costs alone could amount to tens of millions of dollars annually for a large fleet operator. This efficiency gap stems directly from Tesla's unique engineering approach. The vertical integration, the software-hardware co-design, the aerodynamic obsession, and the years of motor and battery development that went into making this truck what it is. Vertical integration is a concept that gets discussed a lot in the context of Tesla's competitive advantages, but it is worth explaining precisely what it means in the context of the Semi. Most traditional truck manufacturers are essentially vehicle assemblers. They design the overall vehicle architecture but source their engines, transmissions, axles, and electronics from specialist suppliers. Each supplier optimizes their component for their own performance and cost targets, but the individual components were not designed together and cannot be optimized together as a truly integrated system. Tesla does something fundamentally different. Tesla designs and manufactures its own motors, its own battery cells, its own battery management systems, its own power electronics, its own vehicle software and firmware stack, its own charging systems, and even its own manufacturing equipment for many of these components. When all of these elements are designed by engineers who share the same data infrastructure and have deep insight into how their component interacts with every other component in the system, the opportunities for system-level optimization are vastly greater than what any assembler working with third-party components can achieve. The 55 kilowatt-hours per mile figure is the direct result of thousands of system-level optimizations that are simply not available to companies that do not control their own technology stack from cell chemistry to software. And then there is the software dimension, which may be the most durable competitive advantage that Tesla has in the commercial vehicle market. The Tesla Semi runs on the same foundation